So here we will consider example for density matrix. Uh, so we can use this density matrix in different um, analysis, statistical analysis, and this is we have to compare that result with the previously obtained result. Then only we can say this density matrix can be used for different applications. So first one we will consider is this an electron in magnetic field model. So this we already did in the statistical mechanics, classical statistical mechanics, and we find out the we found that the magnetic moment is proportion to tan h beta mu v. So that expression, whether we will get the same expression from here or not, that we will check here. So an electron in a magnetic field, that this is a first example where we use the density matrix that we have formulated for the quantum mechanical or quantum statistical mechanics. Okay. So first we will consider this example, an electron in a magnetic field. So here we will consider a single electron with intrinsic spin half h cross sigma, where sigma stands for the Police spin matrix. Okay, so this is half h cross sigma, and then also that electron which is in having a magnetic moment of mu b, and where sigma stands for this Police spin matrix, or sigma cap is stands for this Pauli spin operator, and mu beta is this h cross e by 2 mc. Okay, so this is the these are the initial uh, condition or properties that is associated with this electron, single electron. Okay, so we are considering a single electron in this case, and the spin of that particular electron, which can be up or down depending on that magnetic field direction. So we can choose either it is in the direction of magnetic field or opposite to the direction of magnetic field. So with respect to the direction of magnetic field, so we can say the electron is up or down, and let B is in the direction Z. Okay, in z direction. So then if you take the total energy corresponding to that particular electron which is having spin sigma, and if you calculate that energy, then it is mu b, that is constant, minus mu b, and this times sigma dot p, that is the total energy associated with the electron. And if you take the sigma dot b, then what will be that result? That is, if you take sigma consists of sigma x, sigma y, sigma z. Those are Pauli spin matrices x, y, z in x, y, z. So all those matrices x and y, those take in dot product with bz. Okay, we are considering bz, that is the magnetic field in the z direction. So if you take the dot product with that, that component will become 0. Only that z component remains, that is I dot I, only that same uh, basis vectors, if you consider, or unit vectors, if you consider, that will give you the unity. Okay, otherwise it will become 0 if you take the dot products. For example, I dot j, if you take, that is going to become 0. So similarly we are considering here the magnetic field B is this B is in z direction, so this is bz. So if you take this sigma dot product with this B, only that sigma z B will exist, so that will be sigma z B times 1, and all other terms will become 0. So this is the total energy associated with that particular electron. Okay, now if you consider that Hamiltonian operator H in matrix form, then we can write it like this. Okay, so H, what is the sigma z? Sigma z is nothing but 1 0 0 minus 1, that is Pauli spin matrix z, sigma z. So sigma z is 1 0 0 minus 1, or so if you multiply this value minus b with this matrix, then you will get this matrix. So this is the matrix representation of the Hamiltonian operator. So this is the operator, Hamiltonian operator. Then if you consider the density matrix, we know the density matrix from canonical ensemble. We can write the density matrix like e raised to minus beta h by trace of e raised to minus beta h. This we have already discussed. So in the case of canonical ensemble, we can write the matrix rho, density matrix rho, as e raised to minus beta h divided by sigma e raised to minus beta h, and this sigma e raised to minus beta h we call it as q. That is nothing but the partition function in canonical ensemble, and that is same as the trace of this particular matrix e raised to minus beta h. If you consider that as a matrix, and the if you take the diagonal elements of that matrix, add all those diagonal elements, that is nothing but trace of e raised to minus beta h. That is same of the sigma e raised to minus beta h. If you consider this beta h n, and here we can consider n, then it is nothing but the total of that diagonal elements. Okay, so that diagonal element summation is giving this trace of e raised to minus beta h factor. So the density matrix can be represented like this: e raised to minus beta h by trace of e raised to minus beta h in canonical ensemble. And if you consider e raised to minus beta h, in this particular case, we already know what is h. We have defined h here. This is your Hamiltonian operator in matrix form, and then e raised to minus beta h if you take, then this is the corresponding matrix. So you just have to substitute this particular values mu b b instead of this h. Okay, so that will, here we are having a minus, so first term will become e raised to plus mu b b beta, and the last term, that is fourth term, it will become e raised to minus beta mu bb, because we don't have any minus sign here, but here we are having a minus sign. So if you multiply that, that will become minus beta mu bb. So the second term will become negative when you consider e raised to minus beta h operator, okay, or the matrix. So this matrix is corresponding to e raised to minus beta h, and what you have to take is the trace of that particular matrix. If you consider, first you have to consider, first we have taken this e raised to minus beta h that we have already written here, and now we have to consider the trace of that particular matrix. What is trace of that particular matrix? Trace of that particular matrix is nothing but the summation of the diagonal elements, and that is e raised to beta mu bb plus e raised to minus beta mu bb. And if you divide this e raised to beta minus beta h with the trace of e raised to minus beta h, then you will get the density matrix. So density matrix will be like this: rho is equal to 1 by e raised to beta mu bb plus e raised to minus beta mu bb. This is the trace of that matrix times that particular matrix, e raised to beta mu bb 0 0 e raised to minus beta mu bb. So this is the density matrix representation for that particular case where we have a single electron in a magnetic field B. Okay. Now, if you want to calculate what is the average value of this sigma z, that is the polyspin matrix, that sigma z, that is given by trace of rho times sigma z. If you are having, if you want to calculate the average value of any operator G, then that is nothing but trace of density matrix operator with that particular operator. Okay, this we already did in the previous class. So if you want to calculate what is the average value of sigma z, then you have to consider trace of density matrix rho multiplied with that particular operator. Then what is rho multiplied with sigma z? Rho we already calculated here, you can see here. So rho is 1 by e raised to beta mu bb plus e raised to minus beta mu bb, and that you have to substitute in this expression for average value. So sigma, so rho times sigma z, that is given by this particular expression. This is this much of values are for rho. This is rho, and this is your sigma z. So if you multiply that, only the difference comes If you multiply these two, then it is nothing but e raised to beta mu bb. But when you multiply this row with this column, then you will get an additional minus sign here. So if you multiply those two matrices, and if you look what is sigma rho times sigma z, then we will be having e raised to, this is nothing but your first term, that is 1 by e raised to beta mu bb minus e raised to minus beta mu bb into, this term will become e raised to beta mu bb. This is 0, this is 0, but here we are having an additional minus when you take the product of that row with this sigma z. Okay, so that is rho times sigma z, and if you take the trace of that particular matrix, that is corresponding to the average value of sigma z, then that will be nothing but trace of this matrix is summation of these diagonal elements, but we are having a factor 1 by e raised to beta mu bb by minus e raised to minus beta mu bb outside. So that if you take, then you add, then you can represent it like e raised to beta mu bb minus e raised to minus beta mu bb divided by this common factor e raised to beta mu bb plus e raised to minus beta mu bb. Okay, so I think there is a plus here. Yeah, this is trace of that matrix is plus. So I have written here it is minus, but this is plus. Okay. So here we have that plus. So that is, if you consider this term, then that is nothing but tan h of beta. This is nothing but tan h of beta mu bb, right? If you take sin h of beta mu bb divided by cos h of beta mu bb, you will get this expression. So e raised to beta mu bb minus e raised to minus beta mu bb by e raised to mu beta mu bb plus e raised to minus beta mu bb. So that is nothing but tan h of beta mu bb, and this is what we are getting trace of sigma rho sigma z, and this is nothing but your average value of sigma z, right? That is what we are calculating here. Now the same, if you are calculating this mu z for the case of in case of classical statistical mechanics also, if you calculate mu z, that is the magnetic moment of this electron which is in the magnetic field, and the field is applied in the z direction, what will the magnetic moment in z direction? So that is given by mu b tan h of beta mu bb. Okay, that we already know. And in this case, if you consider what is mu, mu is nothing but ge divided by 2mc, ge divided by 2mc times s, that is s stands for spin, and g is the g factor, and in this case g factor will be 2 for electron with spin. So considering that, that is 2 because we are having up and down possibilities. So the g factor here it is for is 2 for the electron spin, and this s can be replaced with half h cross sigma. As you know, this spin can be replaced by half h cross sigma. Sigma is the polyspin matrix. Okay, so if you substitute this g value in this expression, then we will get mu equal to h cross e by 2mc times sigma, h cross e by 2mc times sigma. And if you are considering mu z, that is magnetic moment in z direction, then h cross e by, this is h cross e by 2mc sigma z. If you take average value of then of this particular expression, then we will get the average value of sigma z here, and the average value of that mu z, that you can write mu z equal to mu b, that is h cross e by 2mc, that is nothing but mu b, and then tan h of beta mu bb that we have taken from here. Okay, so this expression we get, this is same as that of the expression that we got for the so magnetic moments in the in z direction for electron in magnetic field, and when the magnetic field is applied in the z direction. Okay, so we got the same expression as we get as we got in the classical statistical mechanics. Here we are using density by using density machines. Another example or another uh, uh, application, or we can say example, another system where we can apply this density matrix is the free particle in a box of length L. Okay. So in this case we are considering a free particle in a box of length L. Okay, so here the Hamiltonian is H is nothing but minus h cross square by 2m del square, that is the Hamiltonian operator. Okay, and that is nothing but minus h cross square by 2m times dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, so that is the Hamiltonian operator for this particular system, that is nothing but free particle, a free particle. So we are considering single particle here again in a box of length L. Now if you apply this periodic boundary condition for this case, then we can write phi of x, y, z. Okay, that is the uh, coordinates x and x, y, and z. So the if you consider periodic boundary condition, then that is nothing but this will be equal to psi of x, or phi of x, y, z should be equal to phi of x plus L, x plus L, y comma z. So it will be, this should be equal. Okay, x plus L, if you consider psi of x plus L and psi of x, that should be equal. So that is the periodic boundary condition, and in general we can represent this wave function, that is a particle in a box of length L. The corresponding wave function is phi e r, phi e r. This is in spatial distribution, that is nothing but in terms of r. So phi e of r can be represented as 1 by L raised to 3 by 2, 1 by L raised to 3 by 2, that is nothing but a cube root of that L times e raised to I k dot r. This is the wave function corresponding to that particular particle in a box in 3 dimension, in 3 dimension. Okay, in 3 dimension. So that is in 1 dimension, now it will come, this is 1 by root L, right? This is 1 by root L times for example sin n pi x by L, like that. Okay, so the same in 3 dimension it will come like this. A wave function for that particular particle in a 3 dimensional box will be psi r will be equal to 1 by L raised to 3 by 2 raised to I k dot r, and k is the wave vector, E is the energy. Energy is nothing but h cross square k square by 2m. What is k square? How it is coming? This is nothing but p square by 2m. P is h cross k, so h cross square k square by 2m is the energy. So phi at any energy E, which is given by 1 by L raised to 3 by 2 e raised to I k dot r. So this k is corresponding to this particular energy. Okay, so that is the wave function corresponding to that particular particle which is in a box of length L, and we are treating this system in 3 dimensions. Okay, now what is this k vector? K vector, as we can see here, k is nothing but kx, ky, kz. We have three different directions, and in each of these direction we have k values 2 pi by L times nx, ny, nz, nx comma ny comma nz. So in x direction we have 2 pi nx by L, in y direction that is 2 pi ny by L, and in z direction 2 pi nz by L. So that is the wave vector k. Okay, that proof you can get from here. I'm not going to explain that. You can look into this. You can write phi of x plus L comma y comma z is equal to e raised to I k dot r. Instead of k dot r, you can represent it as kx x plus kx L plus ky y plus kz z under boundary condition. Okay, so this should be equivalent to kx x plus ky y plus kz z, because for with one boundary condition psi of x plus L comma y comma z should be equal to psi of x comma y comma z. So this two should be equal, and from that you can reduce e raised to I kxl equal to 1. So kxl will be equal to 2n pi, because e raised to axl equal to 1. This condition will be satisfied when kxl equal to 2n pi. So 2n pi, e raised to 2n pi I is nothing but 1. Okay, so when n should be integer values, n equal to 0 plus or minus 1 plus or minus 2, like that, and that value will be equal to 1. So from that we can get kx equal to 2n pi by L. Similarly for ky also, kz also you can write, this is 2nx. Okay, this is 2nx pi by L. For ky it will be 2ny pi by L, and so on. So that is the expression corresponding to the wave vector in different direction. So now we have to look in the coordinate representation. In the coordinate representation, the density matrix will be having components rho equal to r, rho cap, r cap, sorry, r dash. So this is your the coordinate or the spatial distribution r or wave vector r, sorry, the vector r that represents the position of that particular particle from the origin in 3 dimensions. So that is r, and this is r dash is nothing but the conjugate. So you can see this r and r dash are the position vectors. Okay, and then if you consider this matrix elements, then you substitute this row operator, that is nothing but e raised to minus beta h by trace of e raised to minus beta h. And then if you act that in this particular system, then you can write this r e raised to minus beta h r dash. First we will evaluate this part, that is this numerator part, as you can see from here. So r e raised to minus beta h r dash, that is nothing but e raised to minus beta h. This is same expression. We are just introducing an identity operator here. That identity operator is nothing but sigma e then phi e outer product with the same phi e. So this is nothing but 1. The total value sigma is phi e outer product phi e, that you can this is nothing but completeness rule, and that is equivalent to 1. So we are just putting this particular identity operator here in this expression. Now we will calculate, we will take the sigma e outside of this expression, and then we have r e raised to minus beta e acting on phi e, and we have phi e r dash here. Okay, and this r, this e raised to minus beta e can take outside, and if this r and phi e, if you take this inner products, these two inner products, r phi e and phi e r dash. So what is this? This is nothing but phi e r. This is nothing but phi e r, that is wave function phi with energy e at this position r. Okay. And similarly here also we can see this is nothing but the complex conjugate of this wave function phi e at the position r dash, at the position r dash. Okay, so that is the expression corresponding to this r e raised to minus beta h r dash. And similarly we know this these two expressions, phi e of r is equal to 1 by l raised to 3 by 2 e raised to I k dot r. Phi e r dash, if it is r dash, then we have k dot r dash. Okay, and now we will substitute all those values in this expression, and uh, we get this product in this particular value. So now you substitute those values, these values in here, these two values in this expression. Substitute these two values in this expression. Then what we will get? We will get 1 by sigma k 1 by L cube, because L raised to 3 by 2 into L raised to 3 by 2 will become L cube, and then we have e raised to minus beta h cross square by 2m, that is corresponding to this term. Okay, e raised to minus beta e is nothing but h cross square k square by 2m, and that you substitute here, and then e raised to I k dot r e raised to minus I k dot r dash. And if you further simplify, then you can write 1 by L cube sigma k e raised to minus beta h cross square k square by 2m plus I k r minus r dash. So one of the exponential is gone, and that is taken into along with this other term, and then we'll get this expression in this exponential form, and where k is 2 pi by L times n. Okay, so from this k is 2 pi by L times n. From that you can get this expression L by 2 pi times delta k equal to delta n. And what is delta n? Delta n is nothing but 1, because your n will be having value 0 plus or minus 1 plus or minus 2 plus or minus 3. So the change in n must be unity, because we are considering integer values. So delta n is nothing but 1. Since delta n is 1, L by 2 pi delta k is 1. L by 2 pi delta k is 1. So with that expression, we can write this particular expression L by 2 pi delta k, that is equal to 1. So if you take L cube by 2 pi all cube delta kx delta ky delta kz, we are multiplying all those x, y, z components. So if for each components we are having this L by 2 pi delta k. So that will give you L cube by 2 pi all cube delta kx delta ky delta kz, and this will be equal to 1 into 1 into 1, that is nothing but 1. And if you take 1 by L cube, that is equal to delta kx delta ky delta kz divided by 2 pi all cube, and substitute this 1 by L cube for this value, so that you will get this r e, this is nothing but the average value, e raised to minus beta h, r e raised to minus beta h, that is given by 1 by 2 pi all cube sigma e raised to minus beta h cross square k square by 2n plus I k dot r minus r dash. Okay. And if this L is very large, if the L is very large, what will happen? If the L is very large, these quantities delta kx delta ky delta kz, this will become dkx dky dkz, and that can be replaced as d cube of k for large value of L. Okay. So for large value of L means this quantity is large, 1 by L cube will be small, so this total quantity is very small. So in that condition we can take this d delta k delta kx delta ky delta kz into dkx dky dkz. We are considering very small change here, and a very small change in k, that is d cube k, that is representing that volume. Okay. And this sigma can be replaced with this integration. Okay, this sigma will be replaced with the integration. Okay, and then we can write the expression r e raised to minus beta h times r dash. We can represent this particular expression, which is almost equal to or approximately equal to 1 by 2 pi. We are, because we are considering this condition, so this is an approximation, that is approximately equal to 1 by 2 pi integral of e raised to minus beta h cross square k square by 2m plus I times k r minus r dash d cube k d cube k. I think I have yeah, I think I have missed that value here, right? Delta kx delta ky delta kz, that has to become, yeah, that term also will be here, delta x delta y delta z, right? 1 by L cube I have to substitute, right? Okay, so so this term will come, and then we have correspondingly we have d cube k here, and 1 by 2 pi we are having 1 by 2 pi, and all other terms we have substituted. Okay, so now you just consider this particular expression. I think 1 by 2 pi cube uh, d cube k, and I think 1 by 2 pi cube also will be there, right? Only this term is we are substituting d cube k, integral is changed, and okay. So then we have now each of these integral can be separated with x, y, z. So we are just considering d cube k. So instead of considering all those in a single term, we can separate that in terms of x, y, z coordinates. So for example, if you consider that in terms of x, I can write this expression as e raised to minus beta h cross square kx square by 2m plus I kx into x minus x dash. Similarly, we can write e raised to minus beta h cross square ky square by 2m plus I ky into y minus y dash and so on for z also. So this expression will be equal to e raised to minus root of beta h cross square by 2m kx minus I x minus x dash by 2 times root of beta h cross square by 2m whole square into e raised to minus x dash whole square by 4 times, this is 4 times beta h cross square by 2m. So this is just a simplification or expansion. Actually, you will get the same expression from here. Okay, now that term which is in bracket I have replaced with this u. So e raised to minus u square, whatever we are having this in bracket I have replaced that with the u, and then I can write e raised to minus u square times e raised to minus m. So this 2m you can take that above this expression in this into this portion. Okay, and then 2m 2 and this 4 will get cancelled, then we will get minus x dash square times m divided by 2 beta h square. That is what we have written here. Okay, and du will be getting like this. If u is this total term and if you calculate what is du, then you will get this in terms of dk, and this is in terms of dkx because we are calculating for x direction now. The same expression will come for y and z also. Okay, so the total integral, in the total integral we will be having the same expression with the y and z also. So the integral term, if you consider here, the integral term that is nothing but, what is that? This integral term. Okay, what is, okay, this integral term. Okay, so that integral term I can write. So for we are writing only that x integral term for x variation. Okay, so the integral term will be looking like this. So we are splitting that 1 by 2 pi term also here, or we can take 1 by 2 pi cube also. I think that will be 1 by 2 pi cube, right? Just check that 1 by 2 pi. I think it will be 1 by 2 pi cube. But if you are taking it as a whole for all integration, then it is 1 by 2 pi cube, or if you are taking it for each components x, y, z, then it will be 1 by 2 pi integral e raised to minus u square e raised to minus m x minus x dash whole square by 2 beta h cross square times root 2m by beta h cross square du. Okay, this is the integral term that we will get. And so from this, so actually what we are doing, this dkx I am replacing with 2m by beta h cross square root 2m by beta h cross square times du. Okay, in that integral term, and all other terms are also substituted here, this term, this term. Okay, and this is for x only, x variation in x only. Similarly, we will be having one term with 1 by 2 pi integral e raised to minus u square e raised to minus m y minus y dash whole square by 2 beta h cross square root 2m by beta h cross square du. So that term also will be there, and then multiply with 1 by 2 pi integral e raised to minus u square e raised to minus m z minus z dash square by 2 beta h cross square root 2m by beta h cross square times du. So that u will also change. You can see u, what is u? U is whatever we are writing in this bracket, and for the y and z variations we will be having ky here, y minus y dash here, kz here, z minus z dash here. Okay, so those changes will be there. Okay, so the total integral for x, it will be like this, and then you can simplify this expression. Okay, e raised minus x dash square by 2 beta h cross square. And what is that integration of e raised to minus u square du? E raised to minus u square du, that is nothing but root pi. So minus infinity to infinity e raised to minus u square du, that is nothing but root pi, that we are substituting here. And from that you will get the final expression root m by 2 pi beta h cross square e raised to minus m. So one of this root pi is getting cancelled here. This is root pi, this is pi, so 1 by 2 root pi will come. Okay, and if you take that 2 inside, then this will become 4. 4 and this 2 will get cancelled, so we will be having 2 in denominator. Okay, so that is how this term will come, m by 2 pi beta h cross square, then e raised to minus m, this quantity, okay, this particular quantity. Okay, so that is the integral value for this is for only for x. Okay, so similarly we will be having for y and z also. For y and z also we have to calculate the same, and then you have to get the final expression like this. Okay, for y and z also we calculate, then we will get final expression for this r e raised to minus beta h r dash, that is nothing but m by 2 pi beta h cross square, and this was root, okay, for x only. So if you take y and z also, then that product also will come. So we have this term, this root of m by 2 pi beta h cross square cube, that we have written as 3 by 2. Then this term e raised to minus m, for all x, y, z we are having r minus r dash square by 2 beta h cross square. So that is this term. And what is trace of e raised to minus beta h? Trace of e raised to minus beta h is equal to integral of this term. This is nothing but that elements. Okay, as you know, these are the elements in that particular matrix. Okay, then we'll get the integral of r e raised to minus beta h r d cube r. So if you take this expression, then we will get what we will get. This is if you take the integration, then we will get m by 2 pi beta h cross square raised to 3 by 2, this term as such, and then this term you have to integrate. This term you have to integrate, and when you integrate this term, then that will be giving you this v, right, that particular volume. So that is you can directly take this quantity, you can directly take this quantity, integral of d cube r, that is nothing but your volume v. Okay, so how it is coming like this? Because when you consider for that trace is nothing but the diagonal elements of this set, right? So when you are considering r e raised to minus beta h r dash, this is whole elements. If you consider that matrix, then whatever elements inside that matrix, all elements will be represented by this expression. So first element will be having, for example, r equal to 0, r dash is equal to 0. This is first element for 0 0, and second element is, for example, r equal to 0 and r dash is equal to 1. Just I'm representing that. So that is 1, sorry, 0 1 0 2 and so on, like that, or in this case it is 1 0 1 1 and so on. So that is the whole elements, r e raised to minus beta h r dash represents the all elements in this particular matrix. But when you are considering trace is the summation of all the elements in the diagonal, all the diagonal elements. So only these diagonal elements we have to consider, and in the, when you consider diagonal elements, you have the condition that r equal to r dash. Okay, when r equal to r dash, then only you are taking that trace, right? So when your r is equal to r dash, this term will become 0. This term will become 0, which means that exponential e raised to 0 will become 1. So this term will not exist. Okay, and only you have to take this integration, integral of d cube r, and then that will be your volume. And then if you consider the same, so this is the trace of that particular matrix e raised to minus beta h. This is all the elements in that particular matrix e raised to minus beta h. If you take the trace, then you will get this particular expression. And r rho r dash, now that that is given by, so what is this? This is nothing but trace of e raised to minus beta h. Okay, trace of e raised to minus beta h. This is the matrix, all the elements of that particular matrix r e raised to minus beta h r dash. Now if you take these two, okay, this r e raised to minus beta h r dash by trace of e raised to minus beta h, that is your density matrix with this r and r dash. Okay, so that you will get 1 by v times e raised to minus m r minus r dash by 2 beta h cross square. Okay, so this trace of this is nothing but this expression. Okay, so if you substitute these two expressions in this equation, then we can get it like this. So this is your r rho r dash, that is the elements in that particular density matrix, all the elements in the density matrix, you can see. So if we interchange this r and r dash, what will happen? If we interchange this r and r dash, there will not be any difference for elements in density matrix. Okay, if you interchange this r and r dash, what will happen? So this is your this elements of density matrix. So what will happen if you change this r and r dash? This is the only term with r and r dash. If you change r and r dash, then nothing will happen because we are taking modulus. Okay, magnitude only we are considering, and we are taking the square of that. So this value will not change, which means that interchanging r and r dash will not change the element in the matrix, which means that the density matrix is, again, it is symmetric. In this case also we can see that the density matrix is symmetric. And for diagonal elements, if you consider, which means that when you are having r equal to r dash, if you consider, then that will give you this r rho r, and that is nothing but 1 by v. Okay, that is nothing but 1 by v, because this term will become, this exponential term will become 1 in that particular case, and then you will get 1 by v for r rho r. That is the diagonal element. So all the diagonal elements in in this density matrix are 1 by v. So this is 1 by v, 1 by v, and so on, and all other elements will be 0 it depends. So density matrix, if you consider, in this case also we are having symmetric matrix. Okay, and the diagonal elements value which is equivalent to 1 by v. Okay, so the diagonal elements are independent of r. That means the probability density for the particle to be in the neighborhood, okay, is independent of r. This is independent of r. That is the meaning of this particular expression, that the probability density of the particle to be in neighborhood is independent of r. So that is the particle position. Okay, particles positions are equally likely, which means that all the particles having, if you are considering any particular position, then that position is equally probable for all those particles. Okay, if you are in this case we are considering single particle in that particular box. If you are considering one particular position, that is the probability in that particular position will be equal to the probability in any other position. Okay, so it is independent of r. Whichever r you are considering, it is not does not matter. If you are considering that particle in a box, then if you are considering any position in that particular box, suppose here, or any position, any point you are considering with a different r, does not matter, because your the probability, that is rho r, that is independent of r when you are considering that diagonal elements. Okay, so diagonal elements means the probability density, that probability density is independent of r in this particular case. And then the non-diagonal elements, if you consider non-diagonal elements r dash, then we will get this particular term that we already written, but in that case we are having this term. It is not 1 by v, but we are having this term. So it is giving the measure of probability of spontaneous transition between r and r dash. So in other words, you can say it is the spatial extent of the wave packet from the center of wave packet. It is the spatial extent of wave packet from the center of wave packet. So if you are considering the diagonal elements, then it is independent of r. Then that means the probability density is independent of r in that particular case. But in this case, if you are considering non-diagonal elements, so in that density matrix, what is the non-diagonal elements represent? It represent the spatial extent of the wave packet. So if you, what is that means? If you consider this term e raised to minus, I can write it here, e raised to minus, this is like e raised to minus a times x minus x dash square, something like this, right? All other terms minus m by 2 beta h cross square that I have taken as a. So if you plot this particular graph, what we will get? E raised to minus ax square. That is nothing but e raised to minus ax square. So if you take, for example, x dash is equal to 2 or x dash is equal to, for example, 1, you can take any value. So if x dash is equal to 1, the center point is at 1, okay, and then you change x from 0 to 0, sorry, not 0, minus infinity to plus infinity or whatever it is. So then we will get, when this will become maximum, this will become maximum when this x and x dash are equal, which means when x is equal to 1, this will become maximum. Okay, let's say this is 1, we are not having any amplitude now. Okay, and then on the other either side of this, okay, if x is 1, then this is 0, then e raised to 0 will become maximum, that is 1, value 1. Then if x is equal to 2, then this quantity will be having some value of 1 square, that is 1. So e raised to minus a will be the value when x is equal to 2. So we will be having some less value, right? Some less value on this side. If you consider x is equal to 0, also we will be having minus x1 square. Okay, x is equal to 0. So the same value whatever we are getting here, that will be getting in this side when x equal to 0. So we will be getting something like this, some kind of curve like this, exponential, sorry, Gaussian distribution. This is nothing but Gaussian distribution. So it will not, it will be approaching to 0. Okay. So what it is giving, what this a gives, a constant a will give you the spread of this particular wave function from the center of the wave function. From the center of wave function, how it is spread. If a is small, which means that if you consider this total quantity, if a is small, the spreading will be small. If a is large, the spreading will be large. Okay. Now another case, if you consider the term beta, if you consider beta, if what will happen if beta is large, what will happen? Consider beta, and if beta is large means a is small. Beta large means a total quantity a will become small. So when beta is large, a is small, which means that you will be having some the Gaussian function that will be having small width, right? The width, the spreading will be small. Spreading will be small in that particular case when you are having beta which is large. But when your beta is small, then the spreading will be large. Then what is beta? Beta is nothing but 1 by kt. Okay, beta large means temperature is small. Temperature is small. Temperature small means you will be getting a which is small. So when temperature decreases, your spreading of this wave function from the center, that will be small. Okay, when your temperature is small. And if you take temperature, when temperature approaches to 0, temperature approaches to 0, 1 by kt, this value, what will happen to this value? This value will become infinity, or it is approaching to infinity. When it approaches to infinity, this denominator will be approaching to that infinity, and will be 1 by that infinity approaching, will give you approaching towards 1. The total value of this exponential will be approaching towards 1, which means that your spread will be very small, because you will be having a sharp peak at this one, like a delta function. This will become nothing but a delta function, maximum value at this. So when temperature will become 0, or when it approaches to 0, this spread will be minimum. Okay, then we can locate that particle at that particular position exactly. Okay, so when temperature T tends to infinity, when temperature T tends to infinity, beta tends to 0, T tends to infinity, beta tends to 0, then the spread will become, I think when T tends to infinity, what will happen? T tends to infinity, beta equal to 1 by kt, that is t will become infinity, beta will become 0, right? Then it will become e raised to minus infinity, right? Beta will become, let me check it again. So when t tends to 0, t tends to 0 means 1 by kt will become infinity, beta will become infinity, right? Beta will become infinity. So this term will become infinity. So e raised to minus 1 by, so e raised to, anyway it is by infinity means 0. So e raised to 0, that this quantity will become, um, this quantity will become 1. Okay, in that case it is not going to be a delta function, right? It is not going to, but when your t is going to infinity, then beta will be approaching to 0. Okay, this condition, if you consider t tends to infinity, beta approaching to 0, when beta approaching to 0 means denominator value will be 0, so that this entire quantity will become minus infinity. So e raised to minus infinity to 0 is nothing but 0, so that the spread will become 0. Okay, so this condition, in this condition it will be going to be delta function, it is going to become delta function, right? Yes, this spread is given by this. In the other case, spread will be 1, it is not going to become 0. So in this case it is going to become minus infinity, so the spread will become 0, which means that we will be having a sharp peak at this position 1. So it is going to become a delta function. So what that means, which means that we can find this particular particle at this position, whatever r we are considering here, or r dash that we are considering here, at that position we can find this particle exactly at this position. What this means, the probability is distributed, or there is a spread in that particular probability. The particle can be anywhere in this function, in this particular Gaussian distribution. So it can be in anywhere in this wave function, in this r values, you can see. So any position you can consider within this Gaussian distribution, but in this case you can spot this particular particle at this r dash position. Okay, when t tends to infinity. Okay, so this is not correct. Here t tends to infinity, then we will get this delta function. So when t tends to infinity, we are having that beta value which is going to become 0, and the spread will be minimum, or spread will be almost at approaching to 0, and then we will get that delta function, and the probability will be maximum and equal to 1 at that particular position. So what is happening, the quantum mechanical result will be converting or converging into the classical mechanical result, because in quantum mechanics we are having that spreading, okay, uncertainty in finding that position, but in classical mechanics you can find out the particle at the exact position. Okay, so the quantum mechanical result will be shifted towards the classical mechanics in the limit when t tends to infinity. Okay, so that's about the other elements, off diagonal elements in that density matrix, that will be giving you that spread of that particular um, particle wave function from the central uh, position. Okay, or if you are considering wave packet, it is the from this that center of the wave packet, how much it is spread. So this is the average value of Hamiltonian. So as we discussed earlier, Hamiltonian average, or any operator average, if you want to calculate, then that will be nothing but trace of that operator multiplied with the density matrix. And if you calculate that, you substitute the Hamiltonian expression here. If you substitute that Hamilton expression here, minus h cross square by 2m del square 1 by v times this, okay, that we have already calculated. Okay, and then you substitute that, then you simplify for different x. So you substitute here x minus x dash plus y minus y dash plus z minus z dash, square of all those terms, and then take t cube of r, and then for different values of this dx, dy, dz, you can integrate them separately. And for the first case you have to integrate with dx, then dy, then dyz. So in each cases we have to integrate, and we have to substitute this del value also, dou square by dou x square, okay, dou square by dou x square e raised to minus m x minus x dash square plus y minus y dash square plus z minus z square divided by 2 beta h cross square. This integration, this with the dx, okay, plus dou square by dou y square e raised to minus m x minus x dash whole square plus y minus y dash whole square plus z minus z dash whole square by 2 beta h cross square times dy. Okay, so that integration will also come, plus integral dou square by dou y dou z square, the same term in dy. So all those integration we have to consider. Here I have only given you the for the case of x. So first integration, first differentiation, you take dou square by dou x square, first differentiation of this term, that will give you the value like e raised to minus m x minus x dash square plus y minus y dash square plus z minus z dash square by 2 beta h cross square into minus m by x minus x dash by square by, sorry, there is no square, minus m into x minus x dash by 2 beta h cross square, because this 2, and when you take the derivative of this term, then this 2 and this 2 coming from this term x minus x dash square, that 2 will get cancelled, and you will be getting this particular term multiplied with this exponential term. And in the second case you have to apply the product rule, because you are taking the derivative of these two terms, okay, then you have to apply the product rule. Then the first function you can take like first function as the e raised to minus m x minus x, right, that as first function, and take derivative of the other, or you can take the second one as the first, this one as the first function, and take derivative of this. And if you do this operation, you will get this kind of expression, okay. So I am only representing for the terms of x. Similarly we have y and z, and the first term, if you look, the first term, and if you take the integral after all this calculation, then you can see here e raised to minus m x minus x dash square plus y minus y dash square plus z minus z dash square by 2 beta h cross square plus x minus x dash. This is coming from this second term, okay. This, if you take the differentiation of this one, then you will be getting x minus x dash, right, because the second differentiation, if you take this term times n into x raised to n minus 1, so this is x minus 2 times x minus x dash will come, right. So that x minus x dash will be here, 2 times x minus x dash, and I think that 2 might be cancelled with this 2 beta h cross square. No, yes, this 2 beta h cross square will also come, right. So that will be cancelled. This term, finally you will be having this term, okay, x minus x dash, beta h cross square, m by beta h cross square we have taken outside, so x minus x dash will be there. So x minus x dash, if you consider, similarly we have y minus y dash and z minus z dash term, and when you consider this total integral at x minus x equal to x dash, y equal to y dash, z is equal to x dash, because we are considering this is at r equal to r dash, okay. So r equal to r dash means it is diagonal elements. It is diagonal elements. So x equal to x dash, y equal to y dash, z equal to z dash. If you substitute, all these terms will become 0. Okay, x minus x dash and y minus y dash, z minus z dash, all corresponding terms will become 0. Then only we will be having this term, exponential term. But when you substitute x minus x dash values here, y minus y dash and z minus z dash values here, then this term will become 0. X minus x dash, y minus y dash, z minus z dash, all those values will become 0, and this exponential will be equal to will become 1, and then we will be getting 1 by 2 with beta. So this m will get cancelled, okay, and then we have h cross square and h cross square will get cancelled, and then only we have 1 by 2 v beta, integral of only this 1 plus 1 remains, because we are having e raised to 0 for x, e raised to 0 for y, e raised to 0 plus z. You add all those terms and it will be 1 plus 1 plus 1 dx dy dz. You integrate that, then you will get 3 dx dy dz. Then this integral of dx dy dz is nothing but v. So this v and this v will get cancelled, and finally we will get 3 by 2 times beta. Beta is 1 by kt. Then we will get 3 by 2 kt. This is the internal energy. This is what is average energy of your that particular case. Okay, if you consider particle in that box, this is the average value, 3 by 2 kt. This same expression that you can also calculate by using another formula, which is much more simplified form. You can see here, same expression you will get if you consider the average value of h as trace of h with e raised to minus beta h by trace of e raised to minus beta h. Okay. This also we have, this is also, we know these expressions. We already derived these expressions for average value. That is average value of h is given by, what is average value of h? Average value of any operator if you take trace of rho with that particular operator. And what is rho? You substitute that here, then you will get this expression. Okay, rho is nothing but e raised to minus beta h by trace of e raised to minus beta h. Okay, so then you will get this expression, and this expression I can write minus dou by dou beta of ln of trace of e raised to minus beta h, right? Because when you take this derivative with respect to beta, then you will be getting 1 by trace of e raised to minus beta h times trace of this h. H will come inside, right? H into e raised to minus beta h. Okay, so this expression can be written as this, and then the minus dou by dou beta of ln of v times, if you take this value, substitute the you just substitute the values corresponding to this e raised to trace of e raised to minus beta h, then you will get v times m by 2 pi beta h cross square by raised to 3 by 2, and then simplifying, taking the derivative, then you will get these 3 by 2 by kt, 3 by 2 kt for the average energy. Okay, so that's about the particle in a box case. Now all particle will have this same Hamiltonian. Okay, now we'll consider the system of indistinguishable particles. Indistinguishable particles. So far we have, if you consider the classical particle, they are distinguishable particles. Distinguishable means you can separate them, like by using, for example, 1, 2, 3, 4, etc. So first particle, second particle, third particle, fourth particle. So you can use red colored particle, blue colored particle. So all this way you can distinguish two particles, which means that there will be as a particular property that can be used to distinguish particle. But in this case we are considering indistinguishable particle. Indistinguishable means we cannot distinguish those particles under any kind of property. So suppose we have a gas of n non-interacting particles. Now we are considering n particles. Previously we considered only single particle cases, but now we are considering n particles, n non-interacting particles. Each particle will be characterized by Hamiltonian Hi of Qipi, Hi of Qipi, where I equal to 1, 2, 3 up to n. So the Hamiltonian of each of these single particle is Hi of Qipi, where Qipi are the coordinate and momentum of ith particle. Coordinate, which is the which we already know from that phase space. So that is the spatial coordinate and momentum of the ith particle. Now if you consider any particle, all the particle will be having same Hamiltonian, okay, but they will be having different argument. In that bracket the arguments will be different, but the Hamiltonian form that will be same. because we are considering n non-interacting particles, indistinguishable particles. So let UEI as the wave function or eigenfunction corresponding to the eigenvalue EI, then we can write the Hamiltonian acting on this UEIQI, that is nothing but the eigenfunction. Hamiltonian acting on this eigenfunction will give you eigenvalue EI and the same eigenfunction UEIQI. So this is the Hamiltonian for the single particle. This is the Hamiltonian representing the single particle or the ith particle. Okay. Now for n particle system, if you consider n particle system, then we have the Hamiltonian, which can be represented as summation over I equal to 1 to n for n particle, HIQIPI. Then if you take this particular case, then we can say this is the Hamiltonian for n particles. Then we can say this is the energy for n particle, because when you take the energy summation of all the particles energy, then you have to get the total energy as E. Okay, so then I equal to 1 to n IEI, that will be equal to total energy E, and eigenfunction respective of this or unlike this Hamiltonian and eigenvalue, when you consider eigenfunction, you have to take the product of that eigenfunctions of individual particles to get the total wave function or the eigenfunction. Okay, so total wave function psi of EQ, that will be given by pi I equal to 1, pi I equal to 1 to n, pi for the multiplication, and for all the individual particle wave function you have to take U, E, I, Q, I, and multiply each of them, then you will get the total eigenfunction or total wave function. So the Hamiltonian representing the total n number of particles, that can be Hamiltonian equation. Okay, that is representing total n number of particles, that can be written as this. Okay, so HUEQ, H means total Hamiltonian of the total system for n number of particles. Okay, acting on this psi EQ, which is the total eigenfunction or wave function of that system, which will be equal to total energy times same wave function. Okay, so this is representing the total Hamiltonian of that system or the energy representation. Okay, so the Hamiltonian acting on the psi E, that is total wave function, will be giving you the total energy of the system and the total wave function of this that particular system. Okay, now let there be degenerate state. Okay, if there is degenerate state, this is for non-degeneracy case. If there is degenerate case, then we have to consider psi E as pi m1, pi m equal to 1 to n1. So we are considering n1 number of particles in one state, in for example E1 state, and n2 number of particles in E2 state. Okay, that is degeneracy. More number of particles in one energy level, that is called as degenerate state. So in this energy level E1 we are having n1 number of particles. In E2 energy level we are having n2 particles. Then which means that these energies are degenerate. Okay, so if you are having such a system, in that case your total wave function will be like pi m equal to 1 to n1 u e1 qm. Okay, u e1 of qm, so which means that this is the m equal to 1 to n, means m stands for the particle. Okay, mth particle, which means that it can be first particle, second particle, for third particle, all those particles up to n1 particle, which are at the energy level e1. Okay, e1, so the corresponding the wave function is u e1 of qm. Okay, times, and from that point onwards, from n1 onwards, so we have m equal to next summation, that is n1 plus 1. Okay, after that n1th particle, that is n1 plus 1 to n1 plus n2 total number of particles. Up to that we are having u e2 qm, u e to qm. Okay, so that we have to represent like this for degenerate case, where we have the total ni equal to total number of particles, sigma I equal to 1 to ni, if you take that is total number of particles, and then if you consider sigma I ni ei, that is the total number of particle, total energy, that will give you the total energy, sigma ni I, that is the total energy. Why this Ni? Because we are having degenerate state. Degenerate state. So we will be having, in this case, this E will be equal to, for example, if you consider this case, we will be having, the first case will be N1 times E1 plus N2 times E2. This is the total energy E. Okay, if you are having more number of energy levels with more number of particles, then corresponding energies we have to calculate. So like it will be Ni Ei plus, so in general Ni Ei, so N1 E1 plus N2 E2 plus N3 E3 plus etc. So that is the expression for the case of degenerate state. Okay, so this also you can write it as phi e of q, m equal to 1 to n1 u1 of m. Okay, and then m equal to n1 plus 1, n1 plus 1, n1 to n1 plus n2, n1 plus 1 to n1 plus n2, that is the total number. Okay, so from n1 plus 1 to n1 plus n2, u2 of m. What is u2 of m? u1 of m, you can represent this u1 of m. This is u1 of m. This is, for example, ui of m, if you consider, that is uei of qm. If you are considering ui of m, then it is uei of qm. Okay, so u1 stands for u1 here. u1 of m is nothing but ue1 of qm. ue1 of qm. Similarly, u2 of m is standing for ue2 of qm. Okay, so in that way also you can represent. Let us call this as equation number 1. I hope that is equation number right. Okay. Let's call it as equation number 1. Then now let us consider, now assume a permutation among coordinates. Permutation, I hope you know that permutation, if you are having 1, 2, 3, you can change this position of this. If you consider 1, 2, 3, then if you apply some permutation, let's say 1 and 2, that is changing 1 and 2. So then you will get 2, 1, 3. So 1 changing to 2, 2, 1, 2, 3, 2 changing to 1, then you will be getting 2, 1, 3. Right? That is permutation. So now assuming any permutation, assuming a permutation among coordinates, as a result, this q1 will become p times q1 and q2 will become p times q2. So we are applying some permutation and you are changing this this qm, see this qm coordinate. Okay, so you are changing the coordinate with the permutation, and your coordinate changes q1 changing to pq1 and q2 changing to pq2 after permutation. Then the resulting wave function will be permutation applied on this wave function psi eq. In this wave function you are applying that permutation. After permutation you will be getting m equal to 1 to n1 u1 u1 times, this is qm, this is qm, right? Then u2 times, here we will be having this is this will be changed. This is, we are representing q1 and q2, right? So q1 and q2 times pm, this will be pm, right? This is pm, because we are representing it by using u1. u1 stands for this is ue1 qm. u1 of m is q1 qm. Okay, so q already there, q1 of u1 of m, if you are representing like that, then q will be already inside that. So we can just write q u1 pm, then pi m equal to n1 plus 1 to n1 plus n2 u2 of pm, u2 of pm. So like this your wave function will change after permutation operation. Okay. Now further, if you consider in classical physics, if you consider the classical physics, even though the particles are identical, they are distinguishable. So, in classical physics, if you, or classical mechanics, if you consider, even though the particles are identical, they are identical, but they are distinguishable. Okay, they are similar, but they can be distinguished. Like if you are considering same mass, for example, we are considering 2, 3 balls, okay, instead of particles, and each of these balls are having same mass, same volume, and the same shape. Okay, so that you cannot distinguish these 3 bolts, but they are having different colors. For example, this is blue, this is red, this is black or something. So each of them are distinguishable. They are identical, but they are distinguishable by means of color. Okay, so by means of some property they are distinguishable, but they are identical. Okay, they are similar, but they are distinguishable. So in classical physics, the particles are distinguishable, even though they are identical, but they are distinguishable. So any permutation, if you apply on that state, okay, that result completely a new microstate. That will result in a completely new microstate. For example, if you consider, okay, I will explain this also. For a distribution of Ni, distribution Ni. For a distribution Ni, the possible number of microstate will be capital Ni, sorry, capital N factorial divided by n1 factorial into n2 factorial into n3 factorial, etc. And this particular Wi, which is called as statistical weight factor. This is called as statistical weight factor. That is how many number of ways you can arrange that particular particles in classical system. We are talking about classical system. Okay, for example, if you consider a system with total energy of 4, okay, total energy of 4, and we are having number of particles, total number of particles which are also 4. Okay, then the total energy is 4. So the, let's say the energy levels are like 0 e, 2e, 3e. Okay, so in first case you can consider these 4 energy levels, 0e, 2e and 3e, like this, and you can arrange the particle like, for example, we are having total 4, so and 4 particles are there, so we can consider one particle at 3e energy level and one particle at 1e energy level, and all others there is no particles. So 2 particles at this position. Okay, 2 particles at this position. So these 2 particles have no energy, which means E equal to 0 here. And here it is E, this is 2E, this is 3. So if you consider total energy, this particle is having 3 energy, this particle is having 1 E energy, these 2 particles are having no energy. So total energy will become 4E. This is one state. Okay, one possible state for this particular system. Now if you change the particle, okay, so let's say for better understanding, let's put this as A, B, C and D, A, B, C and D. Now if you change that D and C, you will get same energy. If you interchanging D here, and if you changing this C to that 3 energy level, that will also give you the same energy as 4. Energy will be 4E. Okay, let's say this is 4E. Energy is 4E. Then it will give you same energy for E, but you are changing that particle. Okay, now C is in the top position, and now this distribution will be like this. Your AB is in the same position, A and B are in the same position, and here we are having D. Now D and this is C is changed. C and D are changed, which means one permutation operation is applied in that particular case, which means that these 2 particles D and C are interchanged, but the energy is not changed. but this also will give you another microstate. Now the configuration has changed. Okay, so this is a possible state, this is another possible state, both will give you same energy. So the exchange of particle in classical mechanics or classical system will give you new microstate under permutation operation. So each of these permutation operation, since they are distinguishable, when you apply the permutation result in completely new microstate. A new state or new microstate will be formed for the same system. Okay, so the how many ways you can do this permutations, that is given by this particular expression. So this you just substitute here. N is 4 factorial divided by n1. What is n1? N1 is the number of particles at energy level 1, that is 2. That is 2 factorial multiplied by the second energy level only 1 particle, so 1 factorial, and the third energy level we have no particles here, then we have 1 particle in the third energy level also. So this is the next one, this is 0 factorial, then 1 factorial. 0 factorial is also 1. So all these terms will become 1, and we have only 2 here. So this is 2 factorial is 2 into 1, that is 2. 4 factorial is 4 into 3 into 2 into 1. So this 2 and 2 will get cancelled. So we will having 12 possible ways of interchanging these particles without changing the energy, which means that we are making new states for the particles when they are distinguishable. Each of these interchanging will result in new state or new microstate. So each permutation result in new microstate because they are distinguishable particles. Okay, so by considering the indistinguishability of particles, for example, when you consider the quantum pictures, then where the particles are indistinguishable, okay, when the particles are indistinguishable, Gibbs corrected this particular statistical weight factor by using a factor of 1 by n factorial times the weight factor, statistical weight factor of this classical picture. Then that will be nothing but 1 by n1 factorial times n2 factorial into n3 factorial and so on. And this is true only when this n1, n2, n3, n1, n4, all those values will become 0 or 1. This is only possible when this n1, n2, n3, n4, all those things are equivalent to 1. Okay, so in quantum mechanics, if you consider, in quantum mechanics, an interchange of particle, even they are in different single particle state, that will not lead to a microstate. In quantum mechanics, unlike classical mechanics, if you are interchanging particle, it will not lead to a new microstate. It will not lead to a new microstate. And so the statistical weight factor always in quantum mechanics, that is WQ Ni, this will be equal to 1. WQ Ni equal to 1. This will be always equal to 1. Okay, so if there is any disallowed set of Ni values, which means it is not allowed for that particular state, then the corresponding weight factor, statistical weight factor, quantum mechanical statistical weight factor, WQ of Ni, that will be also 0 if it is not allowed. Okay, if that particular configuration or system or state is not allowed, then that particular corresponding to that, the weight factor will become 0. For all other case, we will be having the weight factor equal to 1. Why it is 1? Because we will not be having any other microstate possible with the permutation. Okay, we are talking about permutation. Okay, so for example, in the case of indistinguishable particle, if you consider whatever you are writing in the previous case, for example, for energy system with the total energy of 4E. Okay, in that case, whatever you are writing as A, B, C, D, that is not possible because these particles are indistinguishable. You cannot write A, B, C, D here, but you can just represent them as with the same notation like this. You have 2 particles here, 1 particle here, and 1 particle here. Now, if you are considering this particle is going up and this particle is going down, that is applying a permutation of changing these 2 particles, that does not change anything in when you are considering indistinguishable particle, because you cannot distinguish this particle whether it is gone up or this particle which is coming down. Okay, we cannot say this particle came down, this particle went up, because we cannot distinguish them. So even they are going up or down, it does not matter, because we cannot distinguish these particles. They are in the same configuration, in the same state. So permutation operation, if you consider in quantum mechanics, or the indistinguishable particle, that will not lead to a new microstate. Okay, so further now, if you consider that equation 1, okay, that we have used to represent the classical wave function for a system of particle, and that is called as the Boltzmannian. Okay, that particular equation can be called as Boltzmannian, and which is not enough to represent a state in the indistinguishable particle with indistinguishable. So if you are having indistinguishable particle, then that particular expression is not enough to represent that particular system, because that particular equation is corresponding to distinguishable particle. Okay, because an interchange of argument, if you consider that equation, I'm not going to express that again here. You just check that equation number 1, you will be having something like u of qm, right? So then you have u of qm again, for example u1 of qm and u2 of whatever it is, or you can just represent it as qi ei, and then u e1 e2, or u I also you can use, whatever it is. But whatever the point is, when you change this qm into the second one, these two qm values, if you change, then that will also give you a new microstate in that particular expression, right? Because here we are having whatever pi, let's say in this case, let's say I changing from, I think it is 1 to n1, then here, sorry, pi, sorry, m changing from, so this is m equal to n1 to n1 plus n2. Okay, this expression. So if you are changing this one with this one, qm to this qm, and then you are changing, interchanging these two, then that also lead to a new state. That also lead to a new state, new microstate. So that particular expression, that is not enough. That is not enough to represent an indistinguishable particle system. So we need another system to represent, or another equation, or the representation for indistinguishable particles. Okay, so the possible representation is a linear combination of n factorial permutations of equation number 2. N factorial permutation is this much number of permutations with equation number 2. Okay, also this combination, when you consider n factorial permutation of equation number 2, along with that we should have this condition, that particular combination should satisfy this condition, that psi square should be equal to mod of p psi square. P is permutation operation. After that permutation operation, whatever value before permutation of operation for this psi square, that should be equal to p psi square. That is, if you are considering psi square, and p psi is the corresponding state after permutation, and if you calculate this one, p psi square, then these two should be equal. These two should be equal. That is the condition. So after permutation, if you calculate after permutation, if you take the mod square of that particular state, and that should be equal to before the mod square of that particular state wave function, that should be equal. Okay, so to satisfy this particular condition, we have two criteria, that is p psi should be equal to psi. First one is p psi equal to psi for all value of p, which means at all permutation operation, if you consider p psi should be equal to psi, and then if it is satisfying this condition, then your psi is symmetric. Psi is said to be symmetric, Another one is p psi equal to psi. It can be psi or minus psi. If it is psi, then which is standing for even permutation, and if it is minus psi, which is nothing but odd permutation. If you are applying p psi, which means that if you are applying permutation operation on psi, and if you are getting psi, then it is called as even permutation. Then p psi, if it is giving you minus psi, then it is odd permutation. It is odd permutation. So first condition is p psi should be psi. Okay, p psi should be psi. In order to satisfy this condition, p psi should be psi. Okay, that is permutation operation on psi will be giving you the same wave function psi for all permutation p, and then psi is, which means psi is symmetric. So psi should be symmetric. At the same time, p psi, it can be psi or minus psi. It can be psi or minus psi. So in that case, it will be having, for example, if you are having even permutation, it is giving you psi. If it is odd permutation, if it is giving you minus psi, then this kind of if it is given like this, then it is called as the psi is antisymmetric. Then psi is antisymmetric. So it depends, which means that if the wave function is depending on the permutation, if you are getting after permutation, if you are getting the same wave function, then it is that particular wave function, it is called as symmetric. If it is giving you psi or minus psi, depending on whether it is even permutation and odd permutation, then that particular wave function is called as antisymmetric. Okay, so if you are considering this case, then we can say psi symmetric. Okay, or you can say u, you can consider u here, usq, that is the symmetric wave function. That will be some constant times sigma p psi times volts of q. Okay, and if you consider this wave function of for antisymmetric wave function, if you consider antisymmetric wave function, then it is nothing but equal to some constant times sigma p. That is, sigma p stands for summation of all that permutation operation, that permutation operation, and we have an additional delta p factor here with permutation on that psi Boltzanian. Okay, Boltz means Boltzanian. So this is Boltzmannian, we already discussed that state, Boltzmannian state, okay, representing psi Boltz representing psi Boltzmannian. So psi Boltzmannian, we are acting that permutation operation on that psi Boltzmannian state, okay. And in this case, we have just that constant. This constant is later we take it as 1. So this is nothing but summation of all those permutation operation and p psi, okay, for that symmetric operation. So this psi will be equal to p psi basically, and here we have u antisymmetric. This is a, okay, u a q, that is equal to some constant, that is 1, for example, or you have to normalize this case. This case you have to normalize that. So we will be having a constant times sigma p, a constant times sigma p times delta p, one additional factor delta p times p psi. This is the permutation operation on that Boltzmannian state, okay, p psi volts of q, and you take all those summation, then you will be getting u antisymmetric. And this antisymmetric means whether this wave function will give you after permutation, it will give you u or minus u, depends on that. Okay, so this that depends on delta p, that depends on delta p, and this delta p can be negative or positive. It can be -1 or +1. It is -1 for odd permutation, and it is +1 for this even permutation. It is +1 for an even permutation. Okay, so depending on that delta p value, this value of u phi or u will become, u will be negative or positive, or you can directly take this as a psi symmetric and psi antisymmetric, psi antisymmetric. Okay, so whether it is symmetric or antisymmetric, it depends on that delta p value. So delta p, we are not giving delta p will be given, or it will be coming after that permutation operation on that Boltzmannian wave function. Okay, so if it is giving minus value, minus p psi, okay, if after this operation, if after this operation we are getting minus psi, then it is corresponding to odd permutation. If it is giving plus psi, then it is coming, it is the even permutation operation. So the antisymmetric wave function, if you apply that permutation in antisymmetric wave function, then it can give you plus value as well as minus value. But in symmetric wave function, it will always give you plus value, positive value, or p psi will be always equal to psi. Okay, there will not be any change when you consider that in the symmetric case. But when you consider the antisymmetric wave function, so depending on that permutation operation, it will be different. If it is odd permutation, then it will be giving you minus psi. If it is even permutation, then that will give you plus phi. Okay. Now, what is the meaning of this even and odd permutations, that I will just discuss. So, if you consider an example, let's consider an example 1, 2. Let's take ABC. Okay. So the possible permutation is 3 factorial here, because we are having 3 different particles ABC. So 3 factorial is nothing but 3 into 2 into 1, that is 6. So total of 6 possibilities for permutation. So if you consider ABC, so this ABC can be represented as ABC, or B first, BAC, and then BCA. Okay, and then you have BCA, then I can write ACB, then sorry, first one is CAB. Okay, that is also possible, CAB, then CBA, right? So all these 6 possibilities are there. 6 permutation operations, 6 total number of permutation is 6. So these are the 6 possible permutations. Okay, and for this case, number of transition, if you consider number of transitions, if you consider, which means from ABC to ABC, how many number of transitions are there? 0. Number of transition will be equal to 0. From BAC, from ABC to BAC, how many transitions are there? Okay, BAC, if you consider, first we have to change A to B, right? Then B to A to B, and B to A. So total number of transitions will be 2. Number of transition will be 2. Okay, and so first we will be in the, for this configuration, what we are doing, we are changing this A to B. So first we will get B, BC, then we will change this B to A. Then that will give you BAC. So 2 transitions, 2 number of transitions. Then if you consider this one, or you can consider this as a transposition. Transposition means we are changing their position. So 2 possible transpositions are there. here we are having BCA. So from ABC, if you are considering how many transpositions are there, first you have to consider A to B, then this A to B, then B to C, then C to A. So three possible transpositions are there. Right? So depending on this number, if you consider, depends on this number of transpositions. So each case we have to calculate this transpositions, then only we'll get this. So here I have made an error because when you convert this, okay, here when you first consider, this transpositions, you will be having. So when you are changing here A to B, right? A to B, A to B. So when you change that A to B, then we'll be getting first one. What we'll get? So interchange. So we'll be getting A to B means BAC, right? BAC will be directly giving you BAC. So only one transposition is enough, right? BAC, only one is enough here. But in this case, when you consider ABC, so to get BCA, first you have to consider A to B. A to B means first we will get B, and this B will become A and C. Then the second one will be, we had to interchange C and A. So second one is C to A, right? So then you will be getting C, B, C, A, right? So two transitions, yes. Two transpositions are there, okay? And similarly, you check for this transposition. So we have 0 and these are even. These are even permutation, and this is odd permutation. If you are getting odd values or odd number of transposition, that is corresponding to odd permutation. Okay, that's all about the permutation. Okay, now if you consider this operation, permutation operation, for the case of symmetric wave function, what will happen for symmetric wave function? That will be us of q, or you can write psi s of q. Okay, so symmetric wave function us of q, this will be, if you consider that operation, that Boltzmannian representation of that state, then you have to take the product of each of these system. So u1, you can consider it as u1 of let's say a, or this one will be a. I will just check that because we will be having the equation like u1 of m, right? u1 of m. So we will be having, let's say, u1 of a, then let's say u2 of b, u3 of c. So like this, you can you have to change its. So this is the first one. Okay, first possible values ABC. Second one is u1 of. You had to check this. I don't know how I wrote this one. Anyway, you can write it later also. So okay. So the second one is B, u2 of A, u3 of C, right? BAC. And third one is BCA. Third one is BCA. I will just write it above. Okay, so in order to see this, so the third one is u1 of BCA, so u2 of C, u3 of A, plus u1 of A, u2 of C, u3 of B, plus u1 of C, u2 of A, u3 of B, plus u1 of C, u2 of B, u3 of A. Just check that. So this is the case for symmetric wave function. This is the case for symmetric wave function us of q. Okay. So whether you consider, here we consider whether it is even parity or odd parity, sorry, even permutation or odd permutation, the sign will be always positive. The sign will be always positive in this case, whether it is even or odd permutation, it does not matter for symmetric case. Okay, but when you consider the same scenario for the case of antisymmetric case, so antisymmetric case, if you are representing this, then u a, or if you can consider psi also, u antisymmetric of q. So what will happen for this case, for antisymmetric? For antisymmetric case, this will be equal to, for antisymmetric, this will be, first case it will be u1 of 1, u1 of A, u2 of B, u3 of C. I am talking about this one. Okay. Then the second one means what? Second one having odd permutation. So when it is odd permutation, the second one will become minus. Second one will become minus because you are having odd permutation. So u1 of B, u2 of A, u3 of C. And what about third one? Third one is even. Third one is even, which means this one. Even, third one is this one. So u1 of B, u2 of C, u3 of A. This is even. So then we are having plus sign here. And then if you are considering next one, if it is odd, then you will be having again negative. So for odd permutation, we will be having negative values. Okay, so let us consider that. So this is even. Then we are having ABC here. So the here what we have to do, B and C only interchanging. So only one. This is odd, right? Then we have ABC. So A to C, A to C. So that you'll get C here and A here. So first one is A to C, A to C, C to A. So this is A. So A to C, then you will get C, B, A. Then you have to change B to A. B to A means C, A, B. And then you have to change B to, sorry, A. Okay, this is right. CAB, right? CAB. Okay. So we have two transposition, which means even. This one is even. Then ABC. First you are to A to C. A to C means again CBA. That is right. So only one. So this is odd. So this is odd. So the third one is odd, then even, then odd. Odd, even, odd. So odd, even, odd. So this one is odd. Next one is odd. So we will be having minus u1 of A, u2 of C, u3 of B. Then plus u1 of C, u2 of A, u3 of B, minus u1 of C, u2 of B, You just check this. U3 of A. Okay. So for even permutation, we are having positive sign, and for odd permutation we are having this negative. So for this case, u or phi a of q, antisymmetric wave function, this will be equal to, or if you consider this particular case, if one interchange any two arguments, in this case any two arguments, in this, if for antisymmetric wave function, for this antisymmetric wave function, if we change any two argument, we will get minus phi. If you are considering this as phi, then it is minus phi antisymmetric of Q. That means antisymmetric in arguments. This is antisymmetric in arguments. Okay. So that you can get from any of this expression. If you interchange any two arguments, if you interchange any two, for example, A, B, C you have considered here. If you interchange this A to B and B to A, whatever you are getting is minus, negative sign. So if you are changing any arguments in two arguments in any two arguments in this antisymmetric wave function, then that will give you minus of that particular wave function, minus psi, which means that particular psi is antisymmetric. This is antisymmetric in arguments. Okay. And further, if you consider, if we consider the same antisymmetric wave function in a determinant form, okay, in determinant form. So let me erase this. So let me put that in determinant form. In determinant form. So in determinant form, I can write this as phi antisymmetric wave function q. This is equal to determinant of. I can write it as u1 a, u2 like u1 same particle, so u1 of b, u2 of c, u2 of a, sorry, this is one, u2 of b, u2 of c, u3 of a, u3 of b, u3 of c. So this is the determinant. Now if you calculate this determinant also, that will give you same expression for antisymmetric wave function. Whatever we have written earlier, same expression that you will get from this determinant. Okay, and so first let us consider, for example, first case, if you consider u1 of a, then you have to calculate this one, right? Multiplied with this cross multiplication if take, then you will be getting u2b times u3c, u2b u3c minus u1 of A, U2 of C, U2 of C, U2 of C, U3 of, right? Same expression you can find in that previous example. And you take all those multiplication, then you will get all those values. So in general, you can write an antisymmetric wave function like this is, you can use U or you can use I here. So this is, so for the case we can consider for single particle wave function as U and the total wave function as psi A. So then we can write this as Ui of A, then Ui of B, or in general I can write this as 1, Ui of 1, Ui of 2, because I had to write it in number form. So Ui of 3 and so on times Un, this is Ui of n, okay, and then we have Uj of 1, Uj of 2, Uj of 3 and so on, Uj of n, and in this determinant finally you'll be having ul of 1. You can denote it with any letter, no problem with that. Ul of 2, ul of 3 and so on up to ul of n. So this is there is also one constant, as you know, we have to multiply this with a constant, we already said, and later if you consider two particle system and you will be getting this constant value, and as a normalization factor like 1 by root n and so on, that we are not going to discuss here. So anyway, so this is the expression or general expression, and general determinant, Slater determinant is called as Slater determinant, and that will give you the antisymmetric wave function. This you have to find out as the normalization factor in that case, whatever system you are considering, and then the corresponding wave function also you have to consider. Then you will get that constant value for the case of antisymmetric wave function. Okay, so what is the importance of this particular wave function? The if you consider the diagonal elements, whatever we are considering the diagonal, I mean the leading diagonal elements, these values, okay, all these values up to this, okay, all the diagonal elements, leading diagonal elements, diagonal elements. So this is nothing but your Boltzmannian, that Boltzmannian system. Leading diagonal elements gives you the Boltzmannian system. Okay, and the interchanging n pair. If you consider other elements also, if you are considering other elements, uh, the other elements or other terms are various permutations. So this is Boltzmannian system, and all other terms, if you consider any other terms, they are representing the other various permutations. And if you interchanging a pair of these arguments, okay, any arguments if you interchange, which means that if you are changing this one with this two, what that means, you are interchanging columns, interchanging arguments, which is nothing but interchanging columns. Okay, interchanging arguments means interchanging columns. Okay, so if two or more particles in the same single particle state, if two or more particles in the same in the same interparticle in the same state particle state single particle state, then the corresponding row becomes equal. Okay, what is this row? This I stands for the same row, right? This all i's. So first row in this case represented by I, and the second row is represented by j. So if you are considering in a single row, if you are considering the first row, which is corresponding to one particular state, single particle state, energy state. So if two particles or two or more particles are there in the same state, which means that we are having two rows with the same values. Okay, which means that two rows are equal. Two rows are equal. If two rows are equal, then the corresponding determinant value will become 0. The determinant value will become 0. What does that means? If you are having same for if two or more particles in same particle in same single particle state, single particle state, then that means corresponding rows are equal. Rows are equal. Corresponding rows are equal. So which means determinant will become 0. Determinant will become 0. That is, determinant becomes 0 means the wave function will vanish. The wave function, total wave function will become 0, or wave function will vanish. So what that means, no two particles or more than two particles should be in the same state. Not two particles or more than two particles should be in the same state. Okay. So there is another representation for the same. So if you consider a system, a statistical system composed of particles obeying Pauli exclusion principle, must be described by a wave function which is antisymmetric in argument. Okay. So if you consider any particles which obey statistical, I will just write it here, statistical system obeying system of particles obeying Pauli exclusion principle, Pauli exclusion principle. So this particle must be described as antisymmetric wave function. Or described by antisymmetric wave function. What is the statement? As we discussed, if the two or more number of particles they occupy in the same single particle state, then this determinant will become 0, which means that there is no wave function, which means that total wave function is 0, which means that the state, that kind of state will not exist. Phi or psi, that wave function representing the total system. Okay, so such a system will not exist. Okay, which means that no two particles or more than two particles will not be in the same single particle state. This is same as that of the Pauli's exclusion principle. So that in Pauli's exclusion principle we say no two electrons will be having same set of all quantum numbers, or they will not be having in this, they will not be in the same state. Same kind of statement we can get from this, that if two particles or two or more particles are in the same single particle state, then the determinant will become 0, the wave function will become 0, or the wave function will vanish. So the determinant equal to 0 means that is corresponding to the antisymmetric wave function. So if you are considering any particles which obeying Pauli's exclusion principle, then they must be represented as a antisymmetric wave function by using antisymmetric wave function. In some other case, we can say the statistics governing the behavior of such particles are called as Fermi-Dirac statistics or Fermi statistics, and the constituent particles are called as fermions. All these those particles which are having this antisymmetric wave function, which also obeys Fermi-Dirac Fermi-Dirac statistics. Fermi-Dirac statistics. Fermi-Dirac statistics, or Fermi statistics, and these particles are called as fermions. Fermions. So for all fermions are represented with the antisymmetric wave function, or all fermions will be having antisymmetric wave function, and those particles which obey or follow this Fermi-Dirac distribution or Fermi-Dirac statistics are called as fermions. Okay, and another type of particles that we have already discussed, the statistics, or the, if you are considering for system characterized by symmetric wave function, for example, we have also discussed this thing for symmetric wave function. Okay, for symmetric wave function, which means that if you are acting that permutation operation, it always gives you positive values. P psi will be always psi. It will not go to the minus or plus like situation. It will be always giving you plus sign. Okay, that is called as symmetric wave function. So for symmetric wave function, or particle obeying this property, or particles represented with the symmetric wave function, this obey Bose-Einstein statistics. Okay, they obey Bose-Einstein statistics, and these particles are called as bosons. These particles are called as bosons. So the thing is that the particles are represented with, or particles which are which can be represented with symmetric wave function, which are called as bosons, and particles which are represented with antisymmetric wave function, which are called as fermions, because bosons obey Bose-Einstein statistics and fermions obeys Fermi-Dirac statistics. Okay, and one more thing that you have to understand here is that for the fermions, they are half integral spin particles. These are half integral spin particles. Half integral spin, like electron, neutron, proton, all of them are fermions. These are integral spin particles. Integral spin particles. Bosons are having integral spin, and the fermions are having half integral. So example for fermions, as we discussed, electron, neutron, proton, or neutrino, helium 3, all those things are this neutrino, etc. All these things are coming in the fermions, and for bosons we are having photons, light particles, the gravitons, mesons, pi mesons. Okay, then phonon is the quantum of sound. Okay, helium 4 is boson, helium 3 is fermion. So all these are they basically, which the particles which are having half integral spin, they will come as fermions. The particle with integral spin, they will come as bosons, and bosons are described in terms of Bose-Einstein statistics. Fermions are described in terms of Fermi-Dirac statistics. And why Fermi-Dirac statistics? All the particles which are having antisymmetric wave function, which obeys Fermi-Dirac statistics, and they are called as fermions. So all the particles which are represented by symmetric wave function, which are obeying Bose-Einstein statistics, which are called as bosons. Okay, so that's all about the indistinguishable particles, and we will take the next section in the next class. Okay.